Hello everyone, I'm Li Yangsun, coming from New York University. I'm currently supervised by Professor Yong Liu and Professor Yao Wang. Today I'm going to talk about our work, flocking-based live streaming of 360-degree video. First of all, I will do a brief introduction to the live 360-degree video streaming system and the challenges it's facing. Then, I will also show how we handle the challenges from three aspects, including collaborative FOV prediction framework, flocking-based strategy, and edge caching. Live 360 video streaming gives users immersive experience, which allows the users to explore what they want to watch. In addition, the video content is delivered in real time. Users can watch the video just right as it happens. The Live 360 video streaming has been applied into many fields, including sport, entertainment, gaming, and education, and I believe there will be more in future. To watch the video, users can use either headset or mobile devices from anywhere. Currently, many companies have been working on Live 360, like Facebook and YouTube. This is a high-level architecture of a Live 360 video streaming system. After an event is captured by the camera, the data is uploaded to the cloud server, where stitching and encoding are operated. Then, users can download the video data to their devices through the internet. Due to the high resolution, it poses high bandwidth requirement on the network. In addition, due to the live property, the end-to-end latency, shown as the time between T2 and T1 in the figure, cannot be too high. To handle the challenges, several works are proposed in these years. Viewport adaptive streaming can solve the bandwidth challenge efficiently, but these works are all about video on demand, not for live. To support viewport-based streaming, FOV prediction is necessary. These works use either self-prediction, which means users make prediction based on past FOV trajectory, or asynchronized collaborative prediction, which assumes FOV data of other users is available. There are also some works about live 360 video streaming. Both of the works here are about system implementation, but not for performance improvement. So, to deal with the challenges, the streaming system should be adaptive. To support it, collaborative FOV prediction is an efficient way. Normally, it is operated asynchronously. When the system is live, which means low latency is required, then the legacy asynchronous collaborative prediction doesn't work. Our work is about how to establish a synchronized collaborative FOV prediction framework for Live 360 and use flocking-based strategy to improve the user's experience. First of all, I will introduce FOV sharing mechanism in Live 360 video streaming system. This is all architecture of the download path of the system, and all the users in this case are watching the same event. In addition, if we assume there's a timeline which shows the latencies of users, the right means early and the left means late. Therefore, user 2 and 3 are with lower latency than user 1 in this case. If user 2 and 3 have watched some video, their true FOV information can be shown as the red and green boxes. Then, they can upload their true FOV information to the cloud server, which can be delivered to the user 1 later. Therefore, we say user 1 can obtain user 2 and 3's ground truth FOV information. The question here is how to utilize other users' FOV information in real time to make better FOV prediction for user 1. The answer is synchronized collaborative FOV prediction, and this is our first contribution. All the users in this case form a flock. I will also show how their experience can be improved by forming a flock. I will also talk about how edge caching can be helpful for the system in the following slides. In this slide, we're going to show how the collaborative FOV prediction works. If we assume user 1 is going to download segment I plus 3, first of all, he predicts the center of the middle frame in segment I plus 3 using his past FOV trajectory. Then, based on the predicted FOV, he can get the predicted attention distribution of the segment. In addition, we notice that user 2 and 3, who are with short latency, have watched the segment I plus 3, and their true attention distribution can be generated. To utilize them, user 1 calculates the distance between his own FOV trajectory with each of the user 2 and 3. Then, we can get a weighted average distribution where the weight is inversely proportional to the distance. At last, user 1 combines his self-prediction and the weighted average distribution into a final one. Then, the video rate is allocated based on that. We do experiments using the FOV dataset, including 48 users for 9 videos, and 1 GB traces to simulate the network environment. Truncated linear is adopted for single-user self-prediction, and the collaborative prediction is a combination of self-prediction and the weighted average of previous users. All the 48 users are randomly divided into 4 latency groups with different initial latencies. We also use KL divergence between the predicted and the true attention distribution as a metric to evaluate the performance of prediction. The results show that for groups with longer latencies, like group 2, 3, and 4, collaborative prediction can reduce the divergence dramatically, which means more accurate FOV prediction. For latency group 1, the prediction performance can be improved with different degrees. Therefore, we clarify that collaborative FOV prediction framework is always helpful to make better FOV prediction. From the same results, we found that front users who are with short latency can only predict based on their own past FOV trajectories. But for the rear user with longer latencies, they can get previous users' information. That is to say, late users can benefit more from previous users. Then, we propose another question: how to further improve the experience for all the users? Our answer is to engineer users' latency by putting strong users in the front. And this is our second contribution, named flocking. In a bird's flock, the strong birds always fly in the front and suffer more air resistance. For the weak birds, they usually fly at the rear and benefit from the strong birds. In a live 360 video streaming flock, we see users with high and stable network condition are strong users. With good network, they don't need long prefetching buffer. Then, the short prediction interval leads to accurate FOV prediction. Besides, we define the users with poor and dynamic network as weak users. Long buffer is required by them to play against the network fluctuation, then leads to less accurate FOV prediction. To solve this, one solution is to let weak users get more ground truth information from previous users. To achieve this, on the timeline, we put strong users in the front with weak users at the rear. Then we evaluate the performance of different solutions. Same as previous, truncated linear is utilized for self-prediction, and collaborative prediction is the combination of self-prediction and the ground truth of previous users. For both self and collaborative prediction, users are given random initial latencies. For flocking strategy, collaborative prediction is adopted, but users are assigned with different initial latencies and buffer upper bounds based on their network condition. From the result, we can still find collaborative prediction is more accurate than self-prediction. In addition, while comparing the flock with collaborative, we find flocking-based strategy can reduce latency dramatically with negligible influence on FOV prediction accuracy. At last, we study the potential benefit of using edge caching for a live 360 video streaming system. Shown in the figure, large volume of traffic might be generated in the core network. To solve this problem, hierarchical caching design can be used. For example, if user 2 generates a request for the data with ID 3 and a resolution of 1080, with caching available, the reply from server can be stored at all the caches along the download path. Later, user 1 requests for the data with same ID but lower resolution. At the cache, if we assume transcoding is enabled, then user 2's request can be served by the cache server so that core network traffic can be reduced. However, if user 3 requests for a high resolution, and we know it's hard to transcode from low resolution to high, therefore, user 3's request cannot be served by the cache, so that traffic cannot be saved in this case. Therefore, we further propose another strategy named enhanced transcoding. With enhanced transcoding, as long as a tile is requested, highest rate is delivered from server to the cache, so that all the following requests for the same tile can be served by the cache. However, enhanced transcoding might consume more storage, so we say it's a trade-off between storage and caching and network performance. To study the trade-off, we do experiments for different strategies, including naive, transcoding, and enhanced transcoding, where naive means transcoding is not available. We use hit rate and network efficiency, which represents the ratio of the data can be saved, to evaluate the performance. The results show that transcoding achieves highest performance when cache size is less than 15 GB. When cache size becomes larger, enhanced transcoding outperforms. To conclude our work, we say that the proposed collaborative FOV prediction framework is always helpful for FOV prediction. In addition, users' experience in terms of video phase can be improved by using flocking-based strategy. At last, we find transcoding at the edge is an efficient way to reduce the traffic in the core network. Thank you very much.